and welcome to our weekly session. I'm Joseph Tuishimire from South Africa. So today we'll be talking about the wetland turbidity using South Africa tools. If I start with the background, you know that we are here to provide some routine data sets. So they are from freely available satellite images. We process them and host them on our web cloud space, and people could access them from there and start doing the analysis, following the trend of agricultural food security, water resource and flood risk, urbanization, land degradation, coastal erosion, and so on. So we have been serving academia, governments, NGOs, even the private sector, and everything is free of charge. So several ways to access our data sets. The first one, the Africa map. It's a very simple area map, which you could do some preliminary analysis, explorations, download data sets, even share results with the whole group. The second one is the Africa Sandbox, which is based in Python coding, which you can do some device analysis and produce some nice graphs, maps, statistics, and then through that net interface, you could even integrate data from your office with the data that's available online via the Africa repository. And you need to create an account. Then you start the analysis. You get both the cloud space and also develop algorithms, notebooks, and with the clear steps. Of course, if you are familiar with some other GIS softwares like QGIS or ArcGIS, you can connect immediately and integrate the data sets from various sources, including ours. Lastly, we support capacity building. We have a full online course through which you offer some courses, how we access our data sets, how we process them, some analysis, even some applications. And later we have some specific courses on water resources monitoring, urbanization, crop monitoring, coastal erosion, and so on. So if you're able to log into our sandbox, you create a free account, you get login credentials, and it's well protected. No one could enter your sandbox account. Then you have access to several notebooks that were grouped by themes. And you see the beginner's notebooks that give you a kind of introduction to Python coding for spatial analysis from non-spatial to spatial analysis. Datasets tells you how we have been processing our datasets and their sources, the accuracy, and so on. Our frequented codes, those are codes that use in our daily life. And those examples, those are codes, notebooks that have been used, and we think they could solve real-time, everyday problems. Supplementary data sets, those are data sets that were got from different providers, and we thought it was better to make them available by our platforms. And some tools, applications that were developed to follow several phenomena. And of course, use cases you could get part to have access to codes that were developed by our users. And after a successful use case, we think we can share them, but they could be either duplicated in other regions or even improved if any user appreciates that. Today we talk about wetland turbidity, and we calculate turbidity in wetlands areas using what you call Normalised Difference Turbidity Index, NDTI. And this is informing us about the optical clarity of the water. So it's not strictly corrected with the transmitted matter, profile content, or the metrics. It is often used in conjunction to provide the more holistic analysis of water quality. NDTI is based on is calculated using the difference between the red and the green bands over their sum. And here we use some annual time series, and we try to understand the clarity of water over time. And the notebook we are using is accessible via our GitHub repository, and I'll be sharing it in the discussion. And as you know, to do all spatial analysis, there are a few things that we should know. First of all, we should know which area we are targeting. So you have taken an example of an area in Senegal, and we should know which package we'll be using. Of course, we should know the time range and also data sets. Yeah, be most using the water observations from space, and of course, trying to plot and even animate what you have. If you load the data set, you could see this is a true color image of our study area in Senegal. And then when load the water observations from space, which is a product, a continental product that was developed by the Africa for long-term water monitoring on the continent. That starts from 1984 to nowadays using Landsat images. When you load it, you see this was mangrove region. We are kind of masking the vegetated area, and we remain with water areas. And if we create the NDTI, this is the time of 13th January 2017. We are comparing it to 5th November 2021, and you could see the large aquatic areas are clearer compared to the smaller one, which are kind of, if you see the NDTI value, and that's where you could conclude after that maybe the large areas may be less affected by turbidity compared to the small areas. And you can produce an animation, a kind of time series showing us the evolution of water turbidity over time. And of course, if we see these large areas are still clearer compared to those small areas, meaning that small water courses might be turbid compared to large areas. And we can investigate the hypothesis. And if you see these topics, this one, this confirms that this is the number of pixels in terms of water coverage, and also could see large water bodies are even allowed below 0 in terms of turbidity, while small water bodies are characterized by a higher turbidity, as you are saying. But yet, we can also try to understand how does it vary by size. Here I've been fixing a threshold of 50,000 square meter, and we mean that everything that be above 50,000 square meter is a large water body, while everything below is considered a small water body. And someone could play with these thresholds depending upon the definition, the local definition of large and small water bodies. And if we try to see the turbidity in using the time series in both large water bodies that's in blue and also small water bodies that's in orange, you could see small water bodies are caused by high turbidity compared to the larger ones. And why? This might be linked to the seasonal variation. You could see if we try to compare the peaks in rainfall with the peaks in water turbidity, we could see that there is a kind of they are kind of matching. With that, during heavy rains, that where the water turbidity might increase, and when the rainfall reduces, also we could see the turbidity is decreasing over time. Now we try to have some examples assessing wetland turbidity. One example was Lake Ngami, it's in Botswana, and through this animation, you could see how the turbidity is increasing. Here they are showing some dates in the months, and the same have done for Lake Bosompre in Ghana, and also could see how the turbidity is going. And for example, if you compare the two lakes, visually you could say Lake Ngami was more turbid compared to this lake Bosompre in Ghana. This lake seems not even turbid compared to Lake Ngami in Botswana. If we go, for example, if we compare Lake Manyara in Tanzania to Lake Oguta in Nigeria, you could see this south eastern part of Lake Oguta, lake seems less turbid compared to this Lake Manyara in Tanzania, which looks more turbid. Sometimes along the edge, even the lake might be turbid for some months or the year. We can also compare the Lake Igis in Senegal and Lake Turkana in Kenya. And if you see, Turkana is more turbid in the northern part. If you can see on the graph, sometimes in this part, but even Lake Igis, the turbidity is also high, and you could see in each lake the turbidity varies with the season. And remember that rainy seasons were created by high turbidity in all our lakes. And the tool has been very useful. Last time, Tamara Manda from Chinua University of Technology in Zimbabwe had an opportunity to present the results of her work using these tools to the 6th conference on the use of space technology for water management that was in San Jose, Costa Rica, early this month. And her study was about Lake Chivelo in Zimbabwe, And you see, this is a very important lake because it is the wetland complex is on the wetland, the Ramsar wetland list, and also it is providing the main water supply for Harare and the habitat for birds. A lot of economic, socio-economic, even biodiversity conservation roles. And over years, the lake has been polluted. There are even the appearance of water ascent. And of course, we think it's a combination of climate change and human activities. And Tamara Manda used the tools to study both the trends in water extent and even the quality over time. And she made a comparison with the rainfall data, and the results showed that drought and other crucial inputs happened in the area, and this could inform not only local population, but the government in decisions they can take in biodiversity conservation, even in the water ecosystem management in the area. And this is some of her results showing using the Ocean Insight tool to be able to identify the trends in open water, that's what that means the water over time, and some green vegetation around wetlands around the lake. That's they seem a little bit stable. Green vegetation seem a little bit stable, and if you see the dry vegetation also seems stable. Even the bare soil under the lake. Those are stages from the lake to the outer, from clear water to bare soil. And if you try to understand the turbidity, you could see sometimes in May to August, the lake seemed a little bit turbid. And of course, this is understanding the lake extent over years, because the lake might shrink or increase in water quantity depending upon the season. And also she tried to understand the eutrophication in the lake using what you call the Normalised Difference Turbidity Index. And you could see the increase in water area corresponds to the increase in eutrophication in the area. If we go to the practical part of this exercise, I told you initially that we can go through our sandbox. When into our sandbox, we have developed notebooks that were grouped into different files depending upon themes, from beginners guide that show us some basics of Python, kind of measuring, loading data, producing plots, intro to number and table calculations. We have also data sets. This show us what the sets we have, how did we access them, or how are they produced, even the accuracy for each data set. We have also to call frequent code. Those are codes we use in daily analysis. And you have the load examples, SDGs, primary data tools, and use case through which you can have some successful examples and codes that was by our users. So today will be the wetland turbidity notebook is found under the yield examples, and it is well developed with introduction. As on notebooks, we start by the title. This notebook talks about wetland turbidity. We have be using Landsat 8, Landsat 9, and the WOFS, water observations from space. That's the product derived from Landsat, and of course, 30-meter resolution. And we'll be calculating the water turbidity using the NDTI index as a proxy. And of course, we are trying to understand how the water seems in terms of clarity. The formula is here, and the publication is here, Loco et al. 2007. And there are steps. You wrote the package you'll be using. We define the area of interest. We mask the area with water using product water observation from space. We plot genetic animations, and of course, we understand the extent over time. As you know, there are some pre-developed packages that could help us to import to DataKeep to do some number analysis, table analysis, to produce plots, and to produce vectors, to calculate the indices, and so on. And the function I'm using is called wetland turbidity, and using this, we'll be able to generate to assess the wetland turbidity over time. So of course, we have to define the boundaries of our study area. So here I've been chosen. I've chosen to use the latitude and longitude in the buffer zone, but you can also upload the polygon if we know the boundaries of our study area. We'll be working on the time from 2017 to 2021. And if we display our coordinates, we have an interactive map showing the study area. And you can we can load our data sets. I told you we'll be loading Landsat data, 30-meter resolution. We'll be using Landsat 8 and 9, and you'll be using the red band, loading the red band, green, blue, and infrared bands. And after loading the data set, with a condition that each image should have less than 10% cloud cover, we find the images, and then we can plot the LEO through color images, and also the water, and this water was generated using, of course, masking the image with a product called WOFS. And you can produce a plot, kind of comparison between our initial time and our last date, comparing the NDTI for 2 different years, and then you can put the animation showing each season of the year, and then we can investigate how does the turbidity correlate with the size of each wetland, and that's why I could see the larger the water body is, the less turbid it becomes, and also small water bodies, of course, are more likely to have a high turbidity. We can try to vectorize and create some thresholds for wetlands that used 50,000 square meter as the threshold. Everything less than the threshold is small water body, and the water body above the threshold is a large water body. We can generate a comparison comparing large water bodies to small water bodies in terms of turbidity, and we see that large water bodies are less turbid compared to the smaller one. We can also compare it with the seasonal valuation, especially considering the rainfall. You see that rainfall months years match with the high turbidity in water in our study area. So this notebook is accessible via our sandbox. And of course, we know that this presentation is short, and that's why we have a training online, self-paced, with a well-detailed videos, tutorials, and it's hands-on exercise. We have two versions, English and French. You get a certificate and even get regular support during the training, and whenever you are stuck, our team is here to support. And of course, could reach out to us using our help desk, even via our website. And of course, this is a good time for the discussion every Wednesday, 11 a.m. GMT. And you see, today it was last time we have been discussing the NDTI animations. Today it's written turbidity in English. Next week that should be the same topic in French, and the same time